New example. Here's the region. It's bounded by these two curves. The axis of rotation is y equal to 1. Here's y. Here's x. This is the line y equal to x corresponding to that. That is the square root function, and we know we're going to need these 2 points, so let's just figure out what they are. At these points, this equation and that equation must be true, so this must be true and that must be true. And since the left hand side is y, x must be equal to square root x. Squaring both sides, x square must be equal to x, or x square minus x must be equal to 0, which means x minus 1 must be 0, so either x is 0 and or x equals 1. If x is 0, then y is 0. If x is 1, y is 1. So there are 2 places at which these curves cross. One is 0, 0, and the other is 1, 1. Okay, so I'm also going to make bold the region that we're going to rotate. The axis of rotation is y equal to 1, so it passes through this point. If I rotate this region around this point, this curve goes up here. And that's the volume of rotation. It's this cone in which we've drilled out this sort of curved funnel. So we follow the same procedure. Here is S along the axis of rotation. The cross section is a washer, and now I have to pick the I have to now find the outer radius of the washer R2, and of course I do that by looking at where the outer radius touches the original region that I'm rotating, and that's down here. So this is R2, and that's the red rectangle up all the way up to the origin of the rotation coordinate system. So this point has coordinates SR2 in the rotational coordinate system, and in the original coordinate system it has coordinates, let's say x2, y2. So this is x2, this is y2. Let's write down the relations between SR2, x2, y2. So S equals x2, and then R2 plus y2 is this entire distance, and that's 1. So R2 equals 1 minus y2, and this point is on this line, so x2 equals y2. Now let's do the same for R1. So from here to here, the inner radius is R1. Let me draw the inner red rectangle. So the coordinates of this point are S, R1. In the rotational coordinate system, x1, y1 in the original coordinate system, and that corresponds to this rectangle. So this is x1 and this height is y1. So let's write the relations for that. S equals x1, S equals x1, and R1, so this is R1 plus y1 must equal 1, so R1 equals 1 minus y1, and this point is on that curve, so y1 must equal square root of x1. Okay, so the one more thing, we need the limits of S. So S equals x2, x2 is this distance, so the smallest value of x2 is this 0, the largest value of x2 corresponds to the x-coordinate of this point, which is 1. So we know the limits of integration as a equal to 0, b equal to 1. The volume is the integral then from 0 to 1 pi r2 squared minus r1 squared ds, and this is pi. I'm pulling the pi out. R2 squared, R2, now I have to get R2 in terms of s. So R2, let me write it here. R2 is 1 minus y2, which is the same as 1 minus x2 because y2 equals x2 and x2 equals s. So 1 minus s. Let's do this as well. R1 equals 1 minus y1, y1 equals square root x1, x1 equals s, 1 minus square root s. So this is 1 minus s squared minus 1 minus square root s squared ds. And now we just have to do that integral. So let me do a couple of steps. Expand the square, 1 minus 2s plus s squared, minus expand this square, 1 minus square root s plus s ds. So this is pi 1 minus 2s plus s squared minus 1 plus 2 square root s minus s ds. This cancels with that. Minus s and minus 2s give us minus 3s. So this is pi integral 0 to 1 minus 3s plus s squared plus 2 square root s ds. And that is, so minus 3s gives me minus 3s squared over 2 plus s cubed over 3 for s squared plus 2 s raised to 3 over 2 divided by 3 over 2 evaluated between 0 and 1, and you calculate that, and that's your answer.